those people online, me and Johnny will be monitoring the chat, so feel free to ask questions.
All right, everyone. Thank you. So today, me and Max are going to talk to you guys about EmitCactus, which is a new tool for. Okay, thank you. Which is a new code generator for CarpetX geared towards CarpetX, right? And so let's start with some physical motivations, right? So our main goal in numerical relativity, of course, is to solve Einstein's field equations for cases where we can't, or it's very impractical to have analytical solutions, or some other approximations won't work, right? And the first step in doing that is to rewrite Einstein's field equations as a Cauchy problem. That basically means that we specify some initial geometrical data on a initial geometrical slice, and we take a number of time steps forward in the future in order to evolve that geometrical data. And initially, right, the first people to create such formulation for GR were Arnowit, Desser, and Misner. They've created the today very famous 3+1 or ADM formalism of general relativity, right? This formulation makes the time evolution character of Einstein's field equations more apparent. And for a long time, the community was not able to do long-term stable numerical evolutions in GR, right? And as time went on, we understood the main mathematical reason why that didn't work. We understood that the ADM formulation is ill-posed, right? And we also understood that the concept of well-posedness is closely linked to that of the hyperbolicity of a PDE system. So in broad terms, we can show that if a PDE system is strongly hyperbolic, it's also well-posed, right? And the BSSN OK formulation, which is named after its creators, Baumgart, Shapiro, Shibata, Nakamura, Ohara, and Kojima. Usually people leave out Ohara and Kojima, but we should really put their names back on, right? It's usually people just say the BSSN formulation. So they came up with a modification of the ADM system, right, that renders Einstein's field equations strongly hyperbolic, and thus finally unlocking that golden objective of long-term stable numerical evolutions in GR, right? So how do we get from ADM to BSSN? Well, so we start easily. We start at step one with the standard ADM formulation, right? Here we have, so like I said, we do a 3+1 split. We have an induced 3 metric on our space-time hypersurfaces, and we have an extrinsic curvature, which basically measures how the normal vector of these hypersurfaces change. We also have the lapse, alpha, and the shift. The lapse and the shift are related to the gauge freedom, the coordinate freedom of general relativity. The lapse basically measuring the distance between hypersurfaces, and the shift, how much a point shifts in between two hypersurfaces, right? So the ADM form makes the time evolution of the 3 metric and the extrinsic curvature really explicit. And accompanying those evolution equations, we have 2 constraint equations. So if you think about electromagnetism, right, the analog to that would be the divergence of the magnetic field equals 0. Well, here in GR, we have 2 such constraints, right? We have the Hamiltonian constraint, and we have the momentum constraint. Okay, so this is step 1. Step 2, we introduce some auxiliary variables, right? So we introduce the trace of the extrinsic curvature, and we introduce the trace-free part of the extrinsic curvature. And after that, we perform a conformal decomposition of the metric, right? What that means is we're going to introduce gamma tilde, and gamma tilde is going to be some conformal factor times your original metric, right? And you're going to promote gamma tilde, a contraction of the Christoffel symbols for gamma tilde, the factor in the conformal factor phi to the trace of k, and a tilde, which is the conformal decomposition of a, 2 evolution variables. And you finally get to the BSSN OK equations, right? So this is a system which contains 1, 2, 3, 4, 5 Did I count that? Yeah, I counted correctly. Right, five equations in its state. Of course, you have to remember that, hidden in here, you actually got, 6 equations because this is a symmetric tensor and so on and so forth, right? And it's a highly complicated system, and it's very hard to do by hand, right? So here you got some details, for instance, the Ricci tensor, which appears here in the evolution for A tilde, right? The Ricci tensor is actually a summation of two different parts, which I have written down here, right? And you also have some details that you have to worry about. For instance, this term here is taking covariant derivatives with respect to the physical metric, but what you really want to do is you really want to rewrite this to be made in terms of your conformal metric and so on, right? So we also get some extra woes. It's not just a simple matter of just writing the equations down and everything will just work. There are lots of tricks and subtleties involved in this, right? Firstly, there are variations of the BSSN system. And one of the most, the community agrees, which is probably the best, which gives you better constraint evolution characteristics, is the W method, right? So what the W method is instead of evolving phi, you evolve W, which is the conformal factor, directly, right? So you get a new evolution equation instead of an evolution equation for phi. But, implicit in this choice, there is a cascade of changes to your equations, right? So because you got a bunch of derivatives with respect to phi, now you're going to have to switch everything with respect to W, and things just become more complicated, more difficult, and more error-prone to do by hand. And code generation comes to the rescue. So the Einstein Toolkit has a rich history of using code generation for lots of things, especially black hole codes, right? So, these difficulties have been pushing us to find code generation solutions for a while now. So one of the workhorses of the BSSN OK codes in the Carpet era was McLachlan. It still is. You can still use it. It's still in the Einstein Toolkit, right? It is generated by Crank, which is a Mathematica-based code, right? You also have other codes in the Einstein Toolkit that solve Einstein's field equations. You have Baikal vacuum, which are generated by NRPy, which is another code generation solution, right? Leeway just told us about his custom code generator earlier today for his subcycling work, right? And continuing in this tradition, we have EmitCactus. EmitCactus is our new generator that really aims CarpetX for now, but it can go beyond that, right? And I think Max is now gonna tell you guys more about it, more about the technical aspects of it.
Yes, hi, I'm Max. I must apologize because this will be a computer science talk for a few slides. So EmitCactus is our code generator for generating complete GPU-ready, SIMD-compatible CarpetX Thorns from a symbolic Python-based DSL. It is a lot like NRPy, it must be said. We took a lot of heavy inspiration from NRPy, and in fact, we use little pieces of it. In EmitCactus, in particular, we use their stencils. And we do plan to accept NRPy LaTeX as an input format, but that's for the future. So as far as goals, we wanted EmitCactus to have a modular design with a strong separation of concerns. We wanted to have an abstract internal representation for all of the math and all of the code. And we wanted all these things because we wanted to make it easier to develop the generator, extend it, maintain it going forward. We wanted to make it easy for people to add their own front and back ends, as well as experiment with different kinds of optimizations. And I'll talk more about all of that in a bit. We wanted more automation. We wanted users to have to spend less time fussing around with the minutiae of developing for Cactus and CarpetX. And we wanted to increase the expressive power of the language. So why not just use Crank or NRPy for these things? Well, Crank is tightly coupled with Mathematica. Mathematica has all kinds of licensing issues, and it's closed source, and generally Mathematica is not a nice language to program in. It's great for symbolic manipulations and not nice to write code in. So we wanted to use SymPy instead of Mathematica. And also Crank is an old code. The developers have pretty much moved on as far as my understanding goes. So maybe it's not maintained as vigorously as it perhaps once was. So NRPy is tightly coupled with SymPy, which is a good thing. That's great. That's also what we do. However, NRPy wraps SymPy's code generation engine, and this didn't give us the level of control over the generated code that we really wanted. And also, SymPy itself has a weakness in that it is not typed. It does not take advantage of Python's new type annotations, and so if you're using a tool like MyPy to statically check your code, then anything with SymPy will have will be a sort of blind spot for MyPy. So we wanted to figure something out to fix that issue. NRPy is missing some key abstractions that we really wanted. I'll talk more about those soon. And also NRPy is concerned about compatibility with older Python versions, which is not a problem. That's a great feature, but we want to be on the cutting edge. We want all those fancy new type annotations that keep getting added in the newer Python versions. So a little more about the separation of concerns. We have divided EmitCactus into three, you could call them stages or modules. So the front end is concerned with taking input. This is the part of the system that you're going to interface with as someone who's writing science code. We call them recipes, but they're the scripts that you write Python SymPy code in. And so that expression, that language, that system you're writing your recipes in is called the EmitCactus DSL. And that's based on SymPy. And as I said, we do want to accept NRPy LaTeX as an input format in the future. The intermediate representation, we have the concepts of the Thorn def and the equation list. So the equation list models your numeric computations as an ordered list of equations. Any kind of computation gets decomposed and modeled as the same way, a series of single assignment statements. And the Thorn def keeps track of everything else, all the other metadata that is needed to generate the Thorn properly. We track reads, writes, we figure out temporaries, we calculate data dependencies, and so forth. And these intermediate representations are agnostic to which front end and back end are being used. The back end, we have the concepts of the generators and wizards. Generators take Thorn def and equation list objects, and they produce abstract syntax trees of CCL files and the source code. What that means is instead of producing text, the generators produce these well-defined tree structures, and that allows us to do all kinds of cool transformations on the tree structures instead of having to manipulate text. And the wizards just take those ASTs and turn them into text for you and output nicely formatted thorns that can go straight into Cactus. And currently, the only backend we have is CarpetX C++. So some more about the DSL. Again, it lets you express your computations as symbolic math. It is strongly typed. We have a layer around SymPy that gives it types. We have ways for you to smoothly interact with other thorns, so you can pull in your variables from ADM BaseX, and you can hook up your state variables to ODE solvers, and you can do regridding and so forth. We have lots of cool tools for expressive power. We support Einstein notation and contracted indices, so if you have a pair of lower and upper indices, it'll expand into the implicit summation for you. You can stay in tensorial notation the whole way. Normally, if you're doing an evolution of a given tensor, we like to imagine that we have a 3D grid where each point contains the tensor, but Cactus doesn't really let you program that way. So when you're writing code yourself, you sort of have to explode all the components of the tensor and put them all into a group. And then, yeah, EmitCactus does all that for you. So you can stay in tensorial notation the entire time. You can use our pre-built stencils, or you can use those from NRPy, or in fact, you can declare your own custom stencils. The default stencil is from NRPy. We have a system for all kinds of cool substitution rules. I'll get more into that soon, but it's a very powerful system. And we are plugged into the Cactus scheduler, so you really never have to touch a CCL file. You can express all of your scheduling needs in the DSL itself. So at this point, I would like to jump out a bit and give a little surface level view of what a very simple wave equation recipe looks like. But before I do that, are there any questions? Yes.
SymPy used to have types. They removed it. Because they weren't happy with NRPy, and they prefer, I think, using Pywrite. Yeah, Microsoft Pywrite utility with that. Will they check types with Pywrite? Yeah. Yeah. Take a look. I sent you a ticket. Oh, sent you a ticket. I sent you the ticket where I actually commented when they removed it. I complained bitterly, but I know what the influence power of the SymPy community.
How can the types be there, but not for NRPy?
Good question. I never supported typing. Just adding private type I would add any identical typing. It's not support any. It was a mistake to add it. They said I ran Pywrite to determine the type completeness of the library. And okay, I see. So actually, we did use PyType, and actually, what the Pywrite does is it tells you how complete typing actually is. Right. In here, where NRPy NRPy itself can be easily blindsided. It's kind of the point.
Yeah.
So we say strong typing, but NRPy can even if you.
Yeah, no, NRPy is not perfect, but
yeah. But it's something good. Also, what version of what quick question would be?
Yes, Zach was telling us about how SymPy used to have types and they were using a different system from MyPy, and that he complained bitterly when the types were taken out of SymPy. It wasn't really a question; it was more of a clarification.
Earlier Python versions. I mean, we only go back to about 3.6-ish.
Yeah.
How far back is this support?
So the question was, how far back in the Python version history do we support? And the answer would be that we are pegged at 3.12 right now. Yeah. Is there a question back there? Yeah. The question was, is it open source? The answer is yes. There's a GitHub link at the end of the slideshow. I just made the repo public, so it probably hasn't been indexed yet, but it is open source. You can contribute and all sorts of nice things. And you can also make tickets to tell us, all the things we need to improve. Okay, so here is a simple wave equation. It's a 2D wave equation in the EmitCactus DSL. I'm not going to spend too much time diving too deep into it because we're going to have a much more in-depth tutorial later, but I will skim over some of the cool syntactic features. The most important thing, you got to construct a thorn def. That's going to be your handle for all things related to the thorn you're generating. Here's an example of some symbol declarations. We just call decal. We give it a name. Here we would specify the indices. In this case, these are scalars, so we leave this list empty. This declaration is redundant. It's been kept there for clarity, but the default centering is VVV. The centering is an important concept for CarpetX. And we bring them, these are symbolic quantities, we bring them into the Python environment, and we can just use them in mathematical expressions once we do this. Here, RHS equals, this is setting up your state variables for ODE solvers. So when you're solving your differential equations, V is declared as a state variable and VT is the right-hand side. That's all you have to do, RHS equals. You don't have to register anything, that's all you do. Here we're declaring a tensor. This is the metric little g. It has two indices, lower I and lower j. The L means lower. If it were upper I and upper j, it would be ui and uj. Symmetries, where this expresses that if you swap these two indices, then the value is the same. Substitution rule, so how I talked about earlier, how you need to explode your tensor components into individual variables in a variable group. there needs to be some kind of well-defined rule for turning the base tensor name into a bunch of C identifiers. And the substitution rule is the mechanism that does this. By default, your substitution rule will be the NRPy notation with U's and D's and then 0 through 2 at the end. But you can override this, and in fact, a lot of cactus thorns, or excuse me, variables from different CarpetX thorns that you may be bringing in and using have a different standard. They use X, Y, and Z. And so actually, if you specify one of those thorns that's known to use that standard, then it will automatically pick the right rule. But you can overwrite it yourself here. In this case, flat metric, we're giving it this matrix. So what we're saying here is that if we index into this tensor at 0, 0, or 1, 1, the value will be 1, and it's 0 everywhere else. So in this case, G gets actually optimized away, and instead we just directly use 1 or 0 because EmitCactus is smart enough to figure that out for you. Lower down here, we add a new substitution rule for the same symbol G, this time with upper I and J with the same matrix. And we're just saying that upper I and upper J for this tensor are the same as the lower ones. Here we're declaring some parameters. It's a similar syntax to decal, and it brings the symbol into the Python environment. However, this also registers it as a parameter that gets put in your param.ccl when that gets generated. Here's just some pure math. We can mix that in with the recipe wherever we want. Kx, speed, ky, these are all parameters we've declared, so these will be set in your par file. And here's just the sympy square root function, and now we have another symbol here. Just grabbing some coordinates. Yes.
So how would you specify the types for the parameter that's default
So the question was, how do you specify the type for the parameters? It's inferred by the default. And I believe there is a way to, oh, that's not what I wanted to do. Turns out the shortcuts on VS Code are different than IntelliJ. Well, if I knew the shortcut in this IDE to show the type information for this function, I would be able to confirm it for sure, but. Oh, okay. Okay, so it's just inferred by the default. You have to give it a default value because param.ccl requires one too, and that by that it will infer the type. Right, so here we're making a function. We give it a name evo because this is our evolution function. We're going to schedule it into evolve.
Strings versus keywords, ranges. I think this is regarding the parameters and their alts and types and stuff.
Yeah, I think right now keywords are not supported, but it would be trivial to add them. We just haven't done that yet. If someone wants that, they should make a ticket on the repo.
So you might do a dimension 4 vector or tensor. Is there like a dimension option when you're declaring like the metric, for example?
So the question was, how do we do different dimensions when we're declaring tensors? You just put more indices in this structure here.
But I mean the dimension, if you had 4 indices instead of 3, like if the range of the indices go from 0 to 3 instead of 0 to 3.
Okay.
There's, that doesn't, there are places where, I mean, there's a set dimension thing, but there are places that don't support that yet.
Okay. If we want like a fluid formula, for example, that wouldn't be.
Yeah, that's not current, that doesn't currently work.
Okay.
Right. So the question was, how do you increase the range of the indices beyond 0 through 2? And the answer is that's not fully supported yet, but we're working on it. Yeah. Of course, this is not finished. You know, we're not done working on it. This is, you know, it's feature complete enough that we were able to write Cottonmouth BSSN okay in it, but obviously we want to keep working on it and adding all kinds of features until it has everything everyone has ever wanted. Anyway, the point I want to make here is just that Currently, CarpetX is the only supported backend, but in theory, there could be other backends. You could target Carpet if you wanted. We could add that, and then you wouldn't have to remember, oh, if I'm in Carpet and versus CarpetX, what's the name of the bin I want to schedule in for evolutions? You just have a generic name. Anyway, here we are adding our equations. This is going to be the computations that we want to evolve. The wave equation looks like this. So, dv dt equals u. V sub t is our right-hand side of v as we declared up here. So we just say add equation vt equals u. Down here, we're saying u sub t is equal to this thing. So remember, g is the tensor we declared earlier. That's the metric. Big D is derivative with respect to Li, and then again with respect to Lj. And because we defined this to have a substitution rule based on a matrix, this actually gets expanded out essentially to this before the code is ever emitted. And down here, so we're initializing the wave just with the analytical solution to the wave equation. We're just setting it here. This is all SymPy stuff, and I think, yeah, we're basing it off of the parameter that we declared and the spatial coordinates we brought in from make chords up here. This part is going to handle regridding. So in CarpetX, if you want to regrid, you bring in this regrid error variable from CarpetX regrid with this specific centering, and you assign it something, and if it's greater than 1, then CarpetX will refine the grid. And don't worry too much about this because this is part of our test suite, but the point you can take from this is that if you have to do any kind of special hackery with scheduling, we do expose that capability. So you can, in fact, emit custom schedule blocks or groups if you need to. And then down here, we're just generating the thorn, the interior sync mode. I'll talk more about that later, but basically you can set different syncing behavior based on whether you want to rely on automatic syncing via presync only, or if you want EmitCactus to emit sync statements in the right spots for you. If you were using, say, mixed error mode. So I can run this. And Python will take its time booting up. And it'll spit out a thorn for us. So here we have our wave equation thorn with all of the CCL files emitted for us. Here's the param file. Again, I'm speeding through this because we're going to have a tutorial about this. So don't worry if I'm going too quickly. I just wanted to show that it does in fact generate a thorn. And I'll show off the evo function just for fun. You can see by this construction that we are using SymD, and you can sort of imagine how the equations we put in got spit out as this, but you can see we're modeling everything based on these single assignment statements. Everything is either a temporary being assigned something or a grid function having something inserted to it or stored to it or read from it. And are there any questions about this before I jump back into the slideshow? Good, okay. Yes. Okay, so moving on from that, I'll talk a little bit about the intermediate representation. So because of the way we do it, because we model the equations in this way and the code in this way, there's a lot of potential for doing cool optimizations based on symbolic and data dependency analyses. Some of the things we've been tinkering with are a way to recycle temporary variables. So we can figure out the lifetime of each temporary, and if one has been read for the final time, we can assign again to it instead of declaring a new one. And in theory, this could reduce register spills on the GPU. We have common sub-expression elimination. We can convert certain expressions into fuse, multiply, add instructions. And in the future, we want to have a system for splitting loops apart. You can do this yourself now by simply moving expensive things into different thorn functions, but we want to have a way of heuristically doing it for you, so you don't have to think about it. The problem is, of course, if your kernel is too big on the GPU, then you overflow the instruction cache and things are slow. And other kinds of optimizations that people care about when they're running code on the GPU. So our system lets us arbitrarily combine these optimizations, reorder them, quickly prototype new ones, all without them interfering with each other, because again, everything is based on tree traversals and tree transformations. And we can do all kinds of correctness checking. I think I forgot to show it, but we figure out how many ghost zones you need based on the tensors, the scalars that you're using, and we emit CCTK asserts in the generated code. So we stop you from accidentally shooting yourself in the foot by choosing ghost zones that are too small. And the read and write decals that CarpetX supports with presync, EmitCactus takes care of that for you. And if you don't want to use presync, then EmitCactus can correctly figure out how to synchronize your state variables and such. A little bit about the backend. Most of this, I think, is repeated information, but we support all of not all of them. We want to support all of them, but we support lots of cactusisms and CarpetXisms. All the code currently is emitted as SIMD vectorized code. We have support for custom stencils. We do everything, we emit all of the CCL files, and we do the same. Yeah, this is all repeated information. I'll just skip this slide. Okay, I'm going to hand it back to Lucas. The computer science talk is over. Back to your regularly scheduled physics talk. Okay.
All right. So continuing on, thanks Max for those details. So I'm gonna give you some more important details, implementation details in Cottonmouth BSSN, our main usage of EmitCactus so far, right? One important trick to keep in mind is that whenever you have terms in the BSSN equations that look like this, what you want to really do is you want to take derivatives of the state variable. Otherwise, you want to use this contraction here. This detail is really important. If you look at the NRPy implementation of this, they even give this a new variable name, right? So, of course, we also do this. And when you do the transformation from ADM to BSSN, you get new sets of constraints, right? Your Hamiltonian constraint, your momentum constraint, of course, are the same, but they get transformed in terms of the new variables. You also get some extra constraints. Basically, that the determinant of your conformal metric is 1, that A tilde is trace-free, and that your contracted Christoffel symbol is equivalent to this term here, right? So the constraints that have a little I symbol on them are just monitored, meaning that we evolve the code and we look at their values, and if they are close to 0, it means that our code is performing correctly. If they start deviating too much from 0, it means our code is not doing so well. So it's an error monitoring technique, basically, right? And G and A are enforced at every grid step, which means that after we take a step, we go back and we modify gamma such that the determinant of gamma is 1, and we modify A tilde such that it's trace-free. Right, and finally, an important piece of information is our gauge evolution scheme, right? So, like I told you guys before, the lapse and the shift are non-physical variables, but we still have to choose how to evolve them somehow, right? And here we're using the standard 1 plus log lapse and gamma driver shift. Now, again, as with anything involving the BSSN formulation, there is a lot of variation in forms of the 1 plus log lapse and the gamma driver shift that we use. So ours is based in the McLachlan implementation of these quantities, right? Here I decided to add, the dissipation factor explicitly just to remind ourselves that we always add dissipation even to the evolution of the gauge variables, right? And now I'd like to show you guys the recipe and some results that we've got on the way of validation for Cottonmouth BSSN, right? So I will switch to my browser. Oh yeah, I was already on my browser. Great. All right, so let's start first, actually. Let's go to the Cottonmouth BSSN recipe. Cottonmouth BSSN is part of the EmitCactus repository, so you can look at it and you can play around with it. So if we go here and we go to BSSN right, we get our main recipe for the BSSN thorn, right? And, some of the pieces here you guys are going to recognize, for instance, the thorn def, we give it an arrangement name and a thorn name. These are just a place where I extracted, so you can control some optimization options in the generation. I just extracted them here into a place just to make it convenient for myself. Noted that, you don't need to set any of these to specific values in order for this to work. It should, this is just we were just testing and messing around with generation parameters. So this is whatever we've left when that was done, right? But I want to call your attention to a few things. So for BSSN, we need to add dissipation. Otherwise, being a nonlinear code, the evolution is unstable. And EmitCactus gives us the ability of defining custom dissipation stencils, right? So here we have a Chrysolliger dissipation stencil that is a 5th order Chrysolliger dissipation stencil, if I'm not mistaken. The stencil itself is only 2nd order accurate, but this is a 5th order derivative, right? So there is a mechanism to add, different stencils using different points. And if you want to do something like that's a lopsided stencil, you could in principle do it, right? So this is very, one of the things that I want to call attention to. Right, we also get the ability of, using some functions, for instance, bringing in some functions that are going to be defined basically at compile time, at C compile time, right? For instance, the max function and other functions as well, right? Here we have some parameters. These are basically just controlling, some gauge evolution parameters, nothing really exciting. For the BSSN system, we have to specify parities. Parities is the way that CarpetX controls what happens when you add symmetries to your evolution, right? How tensors change signs when you add tensors. Yes, there is a, oh, sorry. Yes, there is a question. Dissipation? Sure.
What symmetrize that sense so that you don't push around always from left to right, but rather going in step towards the middle.
So the question was, does the code generator respect parentheses order for instance, if I want to factor a term out of the expressions, would that be respected, right? Right. So this is a code generation question, so the computer scientists will talk.
So the awful thing is SymPy won't respect you if you do that. But we have like a function called no-op that you can just wrap it in and that will propagate a parentheses through. So you can do that, but SymPy kind of fights with you a little bit. Yes, Zach. Right. Actually, now that you say that, I think I do that. We do that too. I don't know if it applies to these kinds of stencils. I know it does with the built-in ones. I'd have to check, but yeah. I did an experiment with that and it didn't help me as much as I thought it would, but anyway.
All right. Do we have any more questions before we go on? Okay, I guess we're clear. All right then. The next feature I want to call after parities, the next feature I want to call attention to is this is just me basically defining all the required variables, the state variables. I also define some temporary variables, which are going to be recycled automatically by EmitCactus, but they're useful to store intermediate quantities. One thing that I want to call attention to is the ability to define custom schedule groups, right? So depending on the complexity of what you're doing, this is actually really required. So for BSSN, we have a certain song and dance of things that we want to happen exactly at when they're supposed to happen. So for instance, you're supposed to enforce your constraints at a very specific moment, right? You're supposed to read your ADM variables and transform them to BSSN variables at a specific moment, and BSSN to ADM also at specific moments. So we define all these custom groups in order to organize our schedule and to make things easier to schedule, right? So I want to scroll down here to where the actual right-hand side of the BSSN equations, evolution equations is implemented, right? And I'd like to call attention. So for instance, if we go to the evolution equations of, for instance, for the right-hand side of gamma tilde, right? What we have here is a pretty direct translation from math into code, right? And things like tensor contractions just work in our system, right? We are able to, for instance, here you have, a derivative of the shift contracted with the derivative index, right? So EmitCactus just understands this sorts of expression and just expand this into the proper things. It also prevents you from doing tensor consistency mistakes. Like, for instance, let's suppose that you inadvertently, you declare this as lower a, lower b, but then your indices for some reason don't match because you've mistyped something, you have a typo, right? EmitCactus will stop you from committing that mistake and will warn you that you should review your things, right? Another important thing just to mention here is that, EmitCactus has these predefined abstract indices, I, J, K, A, B, and C, which you can just use for your expressions as much as you want them to. But you can also call things into specific directions, right? So for here, I wanted to write the dissipation part of this evolution equation, and I wanted to explicitly call our dissipation stencil for GT on X, Y, and Z, right? So L0, L1, and L2 are the ways that we can do that explicitly, right? And I think this is mostly it for the recipe. I would like to show you guys some notebook results now, some validation results that we got from our code, right? So let me just close all this down. I guess this is a good point to check if we have any questions before we move on, either the audience or online. Okay. So the final part of the talk would be, our validation results. I want to show you the most exciting one first, which is this one, QC0.ipy notebook. So what this notebook is going to show you guys is that we have run, a standard QC0 parameter file, 2 binary black holes using 2 puncture data by like 1 point something separation, 0.5 masses, 0 spins. And we ran this for up until like t equal 120 or something, right? And we are comparing our execution against CanudaX again, because CanudaX is a BSSN code ready for CarpetX, right? And here you're using visit for our visualization. So in this notebook, you're going to have access to a sample of the data, not the whole data set because it's just too big, right? We just copied a sample of the data set to the tutorial server, right? And basically what we're looking at here are, our refinement levels of our 2 punctures set up, like how our punctures look like after, some evolution time before coalescing, and then finally, oops, that just jumped. And finally, how they look like after they coalesce, right? And here is the main comparison against CanudaX. So we are comparing here the evolution of the Hamiltonian constraint against CanudaX. So in blue, we got CottonmouthBSSN, and in yellow, we have CanudaX. So we have a slightly smaller error than CanudaX in our Hamiltonian constraint evolutions. We believe that this is because we are not yet doing the advective shift trick, right? So, yeah, sorry. I'm sorry, I've misspoken. So, yeah, I believe that this is because we are not doing the advective shift trick, which basically, when you have terms in the BSSN equations which are of type, beta alpha derivative of alpha, or something that looks like a Lie derivative with respect to the shift vector, you use a lopsided stencil for that. And that it's known to give you better results for the Hamiltonian constraint. We're not doing that yet in our code, right? So we believe that in part that may be one of the main differences that we're looking at. The second thing that, yes, go ahead. Mm-hmm. I do not know. I do not know. So this spike here happens, well, it you do get an increase in Canuda, and then you get, a decrease after that. And since this behavior was consistent across both codes, I didn't initially think that was a problem. I mean, if the spike continued on, and if we didn't go back down again and settled into a value, I think I would be more concerned. But because that behavior was sort of consistent with what we were seeing here, but just seems to be scaled upwards, sort of. I wasn't initially concerned, but I can't give you a precise answer to what that is. Right. Right. So first, let me repeat Helvy's question. Sorry, I haven't. Yeah, no, that's fine. So Helvy asked if we could explain what's happening here between 0 and 25M, where we see these spikes. And after that, Zach asked what volume we are using to compute our L2 norm. So this is CarpetX standard L2 norm computation mechanism. So it uses the whole grid to compute the L2 norm, right? It computes it over the whole domain. It extends from minus 120 to 120. It's a block in this case with 7 levels.
You got excited horizon, Dave's gonna.
Good point. So Zach pointed out that we don't want to compute the L2 norm inside the horizon. And I think the way that CarpetX computes norms, people can correct me if I'm wrong, is that it computes the norms over the whole domain. So it means that it would include the horizons. Right. Right. Okay. So so this is the same information. It's just an absolute differences plot of the same information. The L2 norm with the Hamiltonian constraints compared. Our differences peaking in 10 to the minus 4 or so, right? And here we do a comparison of extracted waveforms. We have psi4 L2 M0 extracted at radius 15 in both codes, right? And here we compare the waveforms. Visually, they look very close to each other. You still can see, a noticeable difference going on here. I believe that in this particular run, we did have new red boundary conditions enabled in CanudaX and not in our code. So that may explain some of the differences we're seeing here as well. And also, the advective shift thing. Again, we have the same information, the absolute difference of the two extracted waveforms, right? So I guess this is the main result that I wanted to show you with our code. We have these promising results. We also, of course, have performed more tests. We have a convergence test. We have a linear wave test. We can go through them really quickly. Right? Oops. But our convergence test is basically showing that we get second order convergence, which is expected because even though our main stencils are fourth order, right, our dissipation stencils are second order accurate, so they are bringing our accuracy down. This is just a standard convergence test done with 2 puncture initial data. We ran then with base resolution to double and 4 times that, and did the standard convergence testing. And for the linear wave test, the point here, right, is to test if your code can actually evolve a linear wave accurately, because you want to extract gravitational waves. And if your code cannot do that, then extracting gravitational waves is going to be difficult. So the test is based on the evolution of this space-time metric, right, which is simple and known analytically. The cool thing about this is that this initial data can also be generated with EmitCactus, and in fact, you're going to find the notebook the recipe, the Python code that generates this thorn here with this analytic initial data in the same folders, right? And what we want with this test is that we want to evolve this for 1,000 crossing times or so, and we want to see if the difference between the evolved linear wave and the analytical linear wave that we get after that time is neither dephased or if doesn't have any major amplitude errors, right? So basically, this is what we get after 1,000 crossing times. Comparing the metric components after the evolution, we get no dephasing and we get close amplitudes, right? This is the same information, but just looking at the absolute differences, right? We're peaking at 10 to the minus 9 here. And I guess, well, we also have performed robust stability tests with our code. You know, it passes the robust stability test. But I guess for validation, these are the main results that I'd like to show. And I guess, let's see, I guess that's it. Oh, and finally, sorry, there's just one more bit. So our initial performance measurements, right? If the slide changes, here we go. So we did some initial performance benchmarkings. You know, this is just really preliminary. We're still profiling and measuring things. But for GPU runs, we found that our right-hand side evaluations, after we made sure that they are doing exactly the same amount of work, you know, initially we had some mistakes in those benchmarks, right? But after we made sure that exactly the same amount of work is being performed across the codes, we got comparable times spent on the right-hand side for both Cottonmouth BSSN OK and CanudaX. For CPUs, we notice an advantage, and we believe that this advantage is probably due to the fact that we emit vectorized code, and that's probably what's doing this difference here on the CPU. Now, these runtimes after 256 iterations are really large on the CPU, but this was run basically on a glorified workstation, right? So this is using, I think, 64 threads in max. So this is why our numbers are so large in comparison to GPU ones. But yeah, these are the initial performance results we have, and these are the results we have for Cottonmouth BSSN OK and EmitCactus. And here's the GitHub link. If you guys are interested, please do check it out and open tickets, and be sure to fill all your concerns and questions. After the break, we intend to give, you know, like a live tutorial on how to use EmitCactus, so that might be cool if you're interested to learn more, how to generate your own thorns and how to do stuff yourself with it, so that you can get a feel for how it works and maybe, you know, start doing some interesting science for yourself with it. And I guess that's it.
All right, so we're ready. We already had lots of questions during the talk, but if there's any straggling ones, we can take a question or two. I can't see online since I'm standing up here, Johnny, if you can check. Okay. Well, then everyone, we will see you back here in 30 minutes, at which point we will have the live demo, and then we will also have a talk by Leo on Grail. So make sure you go get freshened up and come back for more.